Welcome to our comprehensive 4-part series on HAZOP Study. In this first video, we will lay the foundation exploring what HAZOP is, why it is critical, and the core concepts that make it the gold standard in industrial safety. What if I told you that most major industrial accidents, fires, explosions, toxic leaks, were predictable years before they occurred? These catastrophes rarely happen because of a single careless act. They happen because small deviations in the process went unnoticed and unstudied. This is where HAZOP comes in. HAZOP stands for Hazard and Operability Study. It is not just a meeting. It is a highly structured, systematic brainstorming method. Its goal is to identify two specific things: hazards that can cause damage and operability issues that affect productivity. The most important concept you need to understand in Part 1 is design intent. Every piece of equipment in your plant, every pump, pipe, and reactor was designed to operate at a specific pressure, temperature, and flow. This is its design intent. HAZOP is purely focused on one question: what happens if the process deviates from this intent? Unlike accident investigations which happen after a disaster, HAZOP is proactive. It is a documented, risk-driven exercise performed by a multidisciplinary team. It forces us to ask, what if questions long before the plant is even turned on? Because of its effectiveness, HAZOP is the standard in high-risk industries: chemical plants, refineries, power generation, and pharmaceuticals. In these sectors, a small error isn't just an inconvenience. It can be a catastrophe. Most accidents start small: a slight increase in flow, a valve failing to close, a minor instrument error. Without HAZOP, these deviations are invisible. With HAZOP, we catch them before they spiral out of control. That covers the fundamentals. In Part 2, we will dive into the execution. When exactly should you perform a HAZOP, and who needs to be in the room? Stay tuned to build your expertise. Welcome back to Part 2 of our HAZOP series. In Part 1, we covered the theory. Now, we get practical. When exactly should you run a HAZOP? What documents do you need on the table? And who needs to be in the room? A common myth is that HAZOP is a one-time check. It is not. It is a life cycle activity. It starts during the design phase, before a single pipe is laid. It is repeated before commissioning, during major modifications, and periodically throughout the plant's life. Smart plants don't wait for accidents. They study deviations proactively. Before you gather your team, you need data. The golden rule of HAZOP is garbage in, garbage out. If your drawings are outdated, your study will be worthless. You cannot analyze what you cannot see. Essential inputs include up-to-date piping and instrumentation diagrams, PNIDs, process flow diagrams, operating procedures, and material safety data sheets. These documents are the map your team will use to navigate the risks. Now, let's talk about the human element. HAZOP is never a one-man job. It relies on the collective brain. No single person knows everything about the plant. The designer knows the intent, but the operator knows the reality. A typical team includes a HAZOP leader, an independent facilitator who guides the method. You need a process engineer for the theory, an operations representative for practical insight, and experts for maintenance and instrumentation. Different minds see different risks. With the right timing, accurate data, and a diverse team, you are ready to start. In Part 3, we will break down the actual brainstorming process: nodes, guide words, and parameters. See you there. Welcome to Part 3. We've covered the theory and the team. Now we dive into the engine room of HAZOP, the step-by-step brainstorming method itself. This is how we systematically uncover hidden risks. Step 1. Divide the plant into manageable sections called nodes. You can't analyze a whole refinery at once. A node is a logical piece of the process, like the suction line of a pump or a single heat exchanger. This focuses the team's attention on one area at a time. Step 2 is to apply the HAZOP guide words. These are simple but powerful prompts that force the team to think creatively about what could go wrong. The most common ones are no, more, less, as well as, part of, reverse, and other than. Step 3 is to consider the process parameters within that node. For each node, we'll examine things like flow, pressure, temperature, level, and sometimes composition. These are the vital signs of your process. Step 4 is where the magic happens. You combine a guide word with a parameter to create a deviation. For example, If you take the guide word no and the parameter flow, you get the deviation no flow. More plus pressure creates more pressure or high pressure. The team will brainstorm every credible deviation for that node. Let's put it in a worksheet. For node 1, our pump suction line, we apply no to the parameter flow. The deviation to be analyzed is no flow. We've now identified our first potential problem to investigate. We do this for every guide word and parameter combination. That's the core loop. In part 4, we'll answer the next critical questions for each deviation. What could cause it? What are the consequences? And what safeguards do we have? See you there. Welcome to the finale of our HAZOP series. In part 3, we identified a deviation, no flow. But identifying the problem is only half the battle. Now, we must analyze it and fix it. This is where we turn risks into safety. Step 5 is identifying causes. For our no-flow deviation, we ask, why would this happen? Is the pump tripped? Is the suction valve closed? Is there a blockage? The team lists every credible cause, ignoring impossible scenarios like alien invasion. Step 6, consequences. If no flow happens, what is the result? The pump might run dry and overheat. That's equipment damage. But if that pump is cooling an exothermic reactor, no flow could mean a runaway reaction and explosion. We always evaluate the consequence assuming no safeguards work. Step 7, existing safeguards. Now we look for protection. Do we have a low-flow alarm? A high-temperature trip? A pressure relief valve? These are your layers of protection. The team must verify that these safeguards are independent and actually effective. Step 8 is risk ranking. We combine the severity of the consequence with the likelihood of the cause. A high-severity, high-likelihood event puts you in the red zone. This tells management, we need to act now. Step 9, recommendations. If the risk is too high, we recommend action. Install a low-flow trip. Update the operating procedure. Every action must have a responsible person and a deadline. A recommendation without a deadline is just a wish. And there you have it. HAZOP is not just paperwork. It is engineering foresight. It is the difference between a safe shutdown and a disaster headline. If you're an engineer, HAZOP isn't optional. It's your responsibility. Thanks for watching our series. Stay safe.